Hi, Assalamualaikum everybody. We meet again. This is lecture 05 and in this video I'm going to cover on the second part or part B of the second law of thermodynamics. So in this chapter we are going to learn about reversible and irreversible process and also Carnot theorem and equation. First, reversible and irreversible process. If let's say we have a system and this system we provide with heat and the properties inside this system is changing like pressure, temperature or even the phase of the material inside that system. Then after we leave this system at certain period of time, if all the properties that is changing is going back to its initial state, then we call this system is undergoing reversible process. From this example, it brings us to the definition of reversible process, which is a process that can be reversed without leaving any trace on the surroundings. Then we call it as the reversible process. So when a system is undergoing reversible process, both system and also the surrounding will return into its initial state. So this is possible if the net change of the heat and also work between system and surrounding is zero. So basically the reversible process is a very smooth process and this process can be considered as ideal process. And usually this reversible process will produce the best result. And if let's say we are going to create another system, we should refer to this reversible process. If we have reversible process, and of course we will have an irreversible process. So this irreversible process, it is not undergoing reversible process. So that is why we call it as not reversible or irreversible process. This irreversible process, the surrounding will do the work to the system, but that system will not return back to its initial state. So there are several factors that will cause the irreversible process, and this factor we call it as the irreversibilities. So this is the example for the irreversibilities. We have friction, unrestrained expansion, heat transfer across a finite temperature difference, mixing of two fluids, electric resistance, inelastic deformation, and also even the chemical reaction, we can categorize it as irreversibilities. So the concept is simple. If the energy is channeled into one system, but that system is not going back to its initial state, that system is irreversible. For example, mixing of two fluids. We have fluid A and also fluid B. When we mix together, it will not become fluid A and fluid B anymore. It will become fluid C, in which this fluid C is the new properties of that system. So means that it is not going to its initial state, which is fluid A and also fluid B. So this mixing is irreversibilities. Same goes to unrestrained expansion. We have a spring and we pull it until it exceeds its limitation. So that spring will not coming back to its original length. So that spring also undergoing irreversible process. And even the chemical reactions, we are going to react reactant A and also reactant B, and lastly it will produce product C. And if this product C cannot be reversed back into its constituent reactant, which is reactant A and also reactant B, so this chemical reaction is categorized as irreversible process. So for reversible, we have three different types of reversible. First is internal reversible. So this reversible is happening within the boundary. Next, externally reversible, in which no irreversibilities outside the system boundary. And lastly, the totally reversible, where no irreversibilities within the system or its surrounding. So this table is comparing between the reversible and also the irreversible. So this will show you the clear explanation and also comparison between the reversible and also irreversible. Next, we go to Carnot theorem and equation. We have already know the concept of reversible, in which whatever changes experienced by a system, and at the end of the day it will coming back to its initial state, so we call it as reversible. Other than reversible, we can also know that the system is undergoing reversible if it is categorized as Carnot. And this Carnot cycle is actually a reversible cycle. Basically, This Carnot cycle is comprised of 4 reversible processes, which consists of 2 isothermal process and 2 adiabatic process. So let us look one by one the process of Carnot cycle for a closed system. First, process 1 to 2. So this processes is represented by this piston cylinder. From process 1 to 2, we can see here the piston is at position 1, and the surrounding of this piston cylinder, we call it as the energy source, in which it will provide heat into the piston cylinder system, and the heat transferred into this piston cylinder we label as QH. At this stage, even though the heat is channeled into this piston cylinder, the TH inside this piston cylinder, it is constant, it is not changing. So that is why we call the process 1 to 2 is the isothermal. And also, this heat will cause the piston to move from position 1 to position 2. So this process is also isothermal expansion. Next, we go to process 2 to 3, in which the piston cylinder will further move from position 2 to position 3. But at this stage, no Q will be channeled into the piston cylinder, but the temperature inside the piston cylinder is dropping from TH to TL. So for this process 2 to 3, it is undergoing adiabatic expansion. Next, process 3 to 4, the piston at position 3 will go back to the position number 2, but this time we label that position is position number 4. And at this stage, Q from inside the piston cylinder will be channeled out into the energy sink, which is the surrounding. Even though the heat released to the surrounding, the temperature inside the piston cylinder is not changing. So process 3 to 4 is undergoing isothermal compression. Because of this is reversible, it will go back to its initial state, in which it happens at process 4 to 1. At this stage, we can see here from position 4, the piston will go back to its initial position, which is position number 1. And at this stage, no more heat transfer to the surrounding, but the temperature is increasing from TL to TH. Thus, for process 4 to 1, it is undergoing reversible adiabatic compression. From process 1 to 2, and it is going back to its initial state, we can see that it happens smoothly, and whatever work or heat transfer within the surrounding and the system, it will leave no trace. If heat is transferred into the piston cylinder at the first place, but at the end of the day, the Q will be transferred out back to the surrounding. So these Carnot cycle processes can be translated into the PV diagram. The PV diagram for this Carnot cycle is meant for the heat engine, in which we can see here the QH is going in and QL is going out. And also, the processes start with the expansion. If we imagine back heat engine, we start with boiler, and in this boiler, expansion happen, where from water in liquid form, it will be expanded into the vapor or a superheated vapor. So expansion happen, and the expansion happen due to the exposure of heat from outside. Next, from 2 to 3, it happens in turbine, in which when the superheated vapor move the turbine, the temperature will decrease from TH to TL. But at this stage, it happened adiabatically. Next, from 3 to 4, it happened at the condenser, in which at the condenser, the remaining heat that is not transferred into work, it will be channeled out through the condenser into the surrounding. And there we can see QL will be released out from the system. And lastly, it will become compressed liquid, and the compressed liquid will be pumped back into the boiler to start back the process at state 1. So this is for the heat engine. Next, we have also the Carnot cycle for refrigerator and also heat pump. So it is illustrated by this PV diagram of Carnot cycle. And the most significant difference between this refrigerator's Carnot cycle with the heat engine Carnot cycle is the direction of heat, the QL and also QH. For heat engine, QL is going out, but in this Carnot cycle for refrigerator and also heat pump, QL is going in. Same goes to QH. For heat engine, QH is going in, but for Carnot cycle for refrigerator and also heat pump, the QH is going out. when a system undergoing reversible or Carnot cycle, so that system will produce the best efficiency. The efficiency of irreversible process is always less than the reversible process. Even though it is operating under the same reservoir, which is hot and also cold reservoir, if a system it is irreversible, the efficiency must always less than the efficiency of the reversible system. So it is explained in this figure. So I'll give you one example in order to understand this. So if let's say we have one steam plant unit, and this steam plant unit or heat engine is the reversible heat engine. So if let's say we change the entire heat engine with another heat engine, and this heat engine is operated under the same reservoir or the same surrounding. So if we measure the heat engine that we replaced just now, and the efficiency is lower than the efficiency of the heat engine that we replaced just now, so the new heat engine is irreversible. So if we look at this figure, so this 3 heat engine is operated under the same high temperature reservoir and also low temperature reservoir. If they are operated under the same reservoir but the efficiency is different, so we can identify either that heat engine is reversible. These 3 heat engines are operated under the same reservoir, the same high temperature reservoir and the same low temperature reservoir, and the heat engine number 2 is the reversible heat engine, in which this heat engine is the best heat engine because of it is reversible. If we have another heat engine that are operated under the same reservoir, we can identify whether that heat engine is reversible or irreversible. First, we look at the first heat engine. After we measure the efficiency of the heat engine number 1, and it is identified that the efficiency is lower than the efficiency of the reversible heat engine, so this first heat engine is irreversible heat engine. Next, we have another heat engine, and we measure the efficiency of this heat engine, and it is identified that the efficiency for this heat engine is equal with the efficiency of the reversible heat engine. So this heat engine is reversible heat engine. So we can conclude that in order to identify either that heat engine is reversible or irreversible heat engine, we can identify through its efficiency, but by comparing with the efficiency of the reversible heat engine. Next, after we have identified that heat engine is reversible or Carnot, so it has benefits that the QH and also the QL can be related with the TH and also TL. So we can find this QH and also QL in the thermal efficiency equation of heat engine. So this QH and also QL can directly related with TH and TL, and because of that we can replace QH and QL with TH and also TL. So we look at this thermal efficiency equation for heat engine. Originally, it is consists of QL and also QH, and because of this heat engine is Carnot, so the QL and also QH we can replace with TL and also TH. So the thermal efficiency equation, it can be like this: 1 minus TL over TH. But one thing that you have to remember that this T, the unit should be in Kelvin. If you calculate in degree C or any other unit other than Kelvin, so your thermal efficiency is wrong. Just like I explained to you about the figure before, it applies when we measure the thermal efficiency. So we can see here, if we measure the new thermal efficiency by comparing with the thermal efficiency of reversible heat engine, it can be categorized into the following. So if let's say the new heat engine and we measure the thermal efficiency, but the thermal efficiency is lower than the efficiency of reversible, so we call it as irreversible heat engine. But if we measure, then we get the thermal efficiency equal to the thermal efficiency of the reversible heat engine, so we call that heat engine is reversible heat engine. And if we measure the thermal efficiency is higher than reversible efficiency, so it is impossible heat engine, because of we know that the reversible heat engine is the most effective heat engine, so the thermal efficiency should not exceed efficiency of the reversible heat engine. So what I explained to you before is depicted in this figure. If you have 3 different heat engine and the thermal efficiency for reversible heat engine is 45%, if we measure another heat engine and we get the thermal efficiency is 70%, and if we measure another heat engine operated under the same reservoir, so if the thermal efficiency we get 45%, which is lower than the thermal efficiency for reversible heat engine, so this heat engine is irreversible. So if we measure, then we get over than the thermal efficiency for reversible heat engine, so this is impossible. So the thermal efficiency for heat engine operated under the same reservoir, it must not exceeding the thermal efficiency of the reversible heat engine. So CARNOT can be applied into refrigerator and also heat pump. If a unit of refrigerator or heat pump is reversible or CARNOT, so the QH and also QL in the coefficient of performance equation of that refrigerator or heat pump can be replaced with TH and also TL. Just like this equation, the COP for refrigerator usually consists of QL and also QH. So the QH and also QL can be replaced with TH and also TL. So the equation for COP will become like this. The COP of reversible refrigerator, it will become 1 over TH over TL minus 1. And for reversible heat pump, the COP will become 1 over 1 minus TL over TH. So for example, we have reversible refrigerator and we measure the COP for reversible refrigerator is 11. Then if we have new refrigerators operated under the same reservoir or environment, then if we measure the COP, if let's say the COP is lower than the COP of reversible refrigerator, so this refrigerator is irreversible. If it is over, then that refrigerator is impossible. Same as heat engine, the COP of new refrigerator should not exceed the COP for reversible refrigerator if it is operated under the same environment or reservoir. So I think that's all for this video. Till we meet again in the next video. Thank you and Assalamualaikum.